Hello everyone, I am Dr. Nitin Kumar Saxena. In my previous video, I have discussed with you electric field and electric field intensity, how electric field flows from positive charge to negative charge. Now in this lecture, we will discuss what is electric flux, what is electric flux density, and the continuous charge distribution on any surface. So let us start with the concept of electric flux. So to understand the concept of electric flux, we will log it with a flow of wind. Suppose I am saying I am a house and I am considering the ball of this house. Suppose this is a house, and for this house we have, okay, so for this house the wind is flowing like this, right? So if I consider only to this ball is rectangular in shape and the wind is coming from this direction and it will strike to this ball. Now what amount of wind will enter in this house, that will depend on the size of the window, that will depend on the size of the window, right? If the window has bigger size, more wind will come in the house. If the size of the window is very small, less amount of wind will enter in the house, right? So in this way we can understand that this is something which is flowing in the house, that depends on this area, how much area we are going to like, how much area that is like we are going in the direct touch with this wind. Suppose if I am saying, for example, if I am saying, okay, this is the surface, so what will happen if this is the windows, what will happen, the wind will come like this and will enter at this surface. If I am moving this surface like this, so the area is this, now the wind will strike on this area only. And if I am saying when the surface is like this or surface is like this, so this area will be in touch with this wind flow. So in this way we can say that how much amount of wind will enter in the house, that will totally depend on the size of the area which is in contact with this wind, right? In the same analogy, if we talk about the electric field lines which are moving, we know that electric field lines moves from the positive charge to the negative charge. And suppose I am saying this is the electric field lines, right? And for these electric field lines, now what I am saying, for these electric field lines, suppose we have area like this, okay. This is any surface, maybe of any metal, maybe any body, and when this body is in the way of the flow of these electric field lines, then the flux will be defined as that how much area is in contact with this electric field line. Suppose here if I am saying the area of this plate or this surface is suppose A, then and this electric field line's intensity is E. So for this surface, how much electric field lines will interact? They will interact E multiplied with A, right? And this concept is known as electric flux. So we can say that electric flux is defined as the quantity which is going to be which can be calculated by simply multiplying the electric field intensity with the area with which these lines are striking. Okay, suppose if I am saying, okay, look, in the place of like electric field lines are going like this, right, and my area is this one as here. Right, now what I am doing, suppose this is the area, and what I am doing now, this is the area, and now I am trying to rotate this area. I can rotate. If you can suppose any, like if I am saying any piece of paper, it's like this. I can rotate like this. So on rotating this, what will happen? The area which is going to be in touch, which is going to be interact with these electric field lines will change, and hence we can say the direction of the surface will decide how much flux will strike on this surface. So in this way we can say that flux can be defined as the electric field area and cosine of the area. And we can say this is, okay, so we can say that flux can be defined as the dot product between the electric field intensity and the surface area. Dot product. So for dot product, if we solve, then what we will get? EA cos theta. Right. What is the theta? Theta is the angle which is made between the electric field lines and the line of the area, surface area. Now the question comes in mind, what is the direction of the surface area? Right, because if we see this formula, then what we will say, yes, E is the electric field intensity, right, electric field intensity, and A is surface area, and theta is the angle between E and A. Right. So if theta is the angle between E and A, for E we know what is the direction of E. Like E always flows from positive charge to negative charge. So we know the direction of the E. Now the question comes, what is the direction of A? So normally the surface, if we have any surface, then perpendicular direction to the surface is known as the direction of the area. So if I am saying, suppose this is the surface, so for this surface, suppose this is the surface, so for this surface, if we take the perpendicular direction, that will be direction of the A. Right. So if we will change the direction of the A, naturally the flux which will strike on the surface will change, and this is defined as the electric flux. Right. Now the question comes, this phi, like for example, I'm saying, suppose this is the surface, right, this is the surface A, right, this is the surface. So if this is the surface, then you know that total area of the surface is A, and we are saying that the electric field lines are like this, that it's coming towards the direction of the board. So we can say like this, cross. You know, cross means, what is the meaning of the cross? Cross means the electric field lines are going towards the board, right, from this side towards the board. See the direction of my finger. Okay, so it is going inside the board from this direction. So this is the direction of E, right? So we now have the direction of E, direction of A. So this E is I'm supposing this E is uniform for the whole surface. Now I want to know the value of this flux for a unit area, right? If I am saying this is E, okay, and total flux which is striking on this surface, total flux is striking on the surface, on surface A, is phi, right? So I want to know the value for unit area. So what can we say? That flux per unit area, because the total area is A. This term is known as flux density. And since we are talking about electric flux, so electric flux density. Right? So, now you have understood what is electric flux and what is electric flux density. So, the total area which is striking to any surface is called electric flux. Total flux which is striking on this total surface of any total surface, it is known as electric flux. And if we want to define the value of flux which is striking to the unit area is known as the electric flux density. Is it clear? Now see the concept of, if I am saying, okay, the surface is something, surface is something like, okay, we have some figure like this, okay, like this. So you can see for this surface, this is a haphazard surface, and if you see this, so what we can do, we can, like, for our simplicity, we can say, okay, this total surface can be divided in 4 different surfaces. Suppose A1, A2, A3 and A4, right? And similarly, the same thing I am saying here, the electric field which is going towards inside this board is E, and this is uniform. This means the same electric field lines are uniform for the whole surface. Okay, so now I want to know what is the value of flux for this total surface, right? So if I want to know the value of total flux, so what I will say, I'll try to find the total flux will be the flux on surface 1 plus the flux on surface 2 plus flux on surface 3 plus flux on surface 4. This is okay, right? Here you see flux is defined as EA1, EA2, EA3 and EA4, right? So what we can analyze here, that if our surface is not homogeneous, it's heterogeneous. Heterogeneous means the surface is changing place to place, place to place. So what we will do, we will try to find the flux at different surfaces, and finally we will add all of them to find the total value of the electric flux, like this, right? So mathematically we can write it like summation of E into A. We can write summation of E into A. If I'm like, sometimes what we do, we simply say that if we say that, okay, now we are considering the very small part, like this is a very small part of this whole area, and the value of this area is suppose del A, right? So in place of writing A, what we can write? We can write del A. So E del A, right? So this is the generalized formula, that if we have a very small segment of surface area, then we will add all the small segments and we will finally find the value of the total flux. And if we want to write this in the form of the integration, then we can write that yes, phi is integration of E d A. Right? Integration of E, and similarly that the small part is del A, small part is del A, so the total is E del A. And if I want to remove this vector sign, then I can write E cos theta dA. So this will be the value of total flux. That the formula which we have derived here for electric flux, it would be very useful for the next topic which we will discuss in next lecture, the Gauss law. How can we find the value of electric field using this Gauss law? That we will see in next lecture, and at that time we will use this formula. So this formula is very useful when we will talk about the Gauss law. Is it okay? Now after this, in this lecture, we will go for the next topic is continuous charge distribution. Continuous charge distribution. Okay, like in our study we have like considered that we have a point charge. Point charge means that all the charge is confined at a single point, suppose plus q, which we have shown in different studies. But practically, if you see any surface, for any practical surface, there is no significance, or there is no existence of a point charge. The surface may be linear type, maybe a line type, maybe a surface type, a two-dimensional. You know that we have three things: unit 1D, 2D, or 3D. We can draw the different figures with the help of either single diagram, one dimensional, two dimensional, or three dimensional, right? So any figure in real, any realistic figure may be either one dimensional, two dimensional, or three dimensional. So what does it mean? It means if we have the figure one dimensional, so it has the charge on this one dimensional figure. Two dimensional, so it has the charge on two dimensional figure, and if it is three dimensional, it has the charge on three dimensional figure, and which is distributed all over the surface of the this object or figure or body. We cannot consider it as a point charge, right? Suppose if I am saying we have a line charge. Okay, so I am saying the line charge is plus q, mean to say that we have a charge is distributed along a line, right? So what is this? This is called one dimensional figure, and for this one dimensional figure, the total charge is distributed along this line, right? Similarly, if I am saying suppose a square or rectangle or circle, so these all are the two-dimensional figure. So if this is two-dimensional figure, so what we will say that the charge plus q is distributed on this surface, right? On this surface. And if I am saying the three-dimensional figure, suppose something like a square, sorry, cube or cuboid or sphere, right? So cube, cuboid or sphere, these are the surface which has volume, or they are the three-dimensional. So the total charge will be distributed on the volume. So you see here the charge is distributed on the line, so we can say the charge is distributed on the length of the line. Here charge in two-dimensional figure, the charge is distributed on the surface of the body in two-dimensional, and in three-dimensional the charge is distributed on the whole volume, right? So normally we have the total charge. Suppose if I am saying the total charge on this surface is the same. I am using del q here, and del q here. So del q is the total charge on one-dimensional surface, two-dimensional surface, and three-dimensional surface. And you know that this is the uniformly distributed surface. So it's for such type of surface, in place of giving the value of the charge total, we define these values in terms of density. And what is the term of density? You see here we can define it like this. one dimensional, we define linear surface density, right? Similarly, for two dimensional, we define what we define surface, because I told you that all the charge is distributed on the whole surface. So we define surface, linear charge density. This is linear charge density. Okay, for one dimensional, what we defined a term linear charge density. For two dimensional, we defined a term surface charge density, and for three dimensional, we defined a term volume charge density, right? Because in one dimensional, the total charge is distributed along a line, so we say this linear charge. And linear charge density means that if we have total charge is del q, right, and the length is considered that for this line surface, one dimensional surface, the total length is del L, so we can define like this: del L, del Q divided by del L. So this term del Q over del L is defined as linear charge density, and normally it is represented by the term sigma, right? Similarly, if we go for this two-dimensional figure, I told you that for two-dimensional figure, the total charge is distributed on the surface, and surface means the surface area. So surface area, if I am saying the total surface area is suppose del A, so this will be the surface charge density, and normally we define it by lambda, right? So what is lambda? Surface charge density, and its value is del Q over del A, right? Similarly, if you go for three-dimensional figure, the total charge is distributed on the volume of this three-dimensional figure, right? So if I am saying the volume is del V, so total charge for per unit volume is defined as volume charge density, and it is represented by rho, right? So in short, we can say that linear charge density is defined as the charge per unit length. So this is the charge per unit length surface charge density is the charge per unit area and volume charge density is charge per unit volume. Right? The term linear charge density is defined by sigma, the term surface charge density is defined by lambda, and the term volume charge density is defined by rho. Right? This is clear. So next step, we can find the unit of sigma. What is the unit of sigma? Sigma is del Q by del L. Lambda is del Q by del A, and rho is del Q by del V, right? So what would be the value of unit for sigma? This will be coulomb per meter. For lambda, coulomb per meter square or square meter, and coulomb per meter cube or cube meter, right? So these will be the unit for sigma, lambda and rho. So I hope the continuous charge distribution is clear to you, that what is the repeating again in a very quick way, that continuous charge distribution, okay, continuous charge distribution. So how can we define continuous charge distribution? That any surface may be either one dimensional, two dimensional or three dimensional. So charge is distributed on the whole surface, maybe linearly if one dimensional, on the surface area if two dimensional, and on the volume if three dimensional. So in place of defining the total charge, we try to define the value in terms of density. If we are talking about the one-dimensional figure, means it has only the linear term. So what we will say, for linear charge density means the charge per unit length. And this charge per unit length is defined by sigma and its unit is coulomb per meter. Similarly, for two-dimensional, the total charge is distributed on the surface area. So this is defined as charge per unit area. It is represented by lambda and its unit is coulomb per meter square. And if for three-dimensional figures, the total charge is distributed on the whole volume of the surface on the body. So if we define the volume charge density, so volume charge density is what? Del Q over del V means the value of the charge per unit volume. And this charge per unit volume is defined by rho and its unit is coulomb per meter cube. Okay, so I hope the concept of electric flux and the value of the electric flux for non-homogeneous surfaces, how can we find by integrating it, and what is the value of flux density, and finally how can we define the continuous charge distribution. This we have discussed in this lecture. I hope you have understood it and you enjoyed it. Thank you very much.